Today's lesson is going to look at how to use hypothesis tests to compare means of two different populations. So these two different populations could be if we're talking about people, two different locations, or maybe the same population but at two different points in time, to see has there been a significant change. So with these, we're looking at differences, how much these differ from each other. So just like with the plain means test, where we're doing a test about the mean, we have two different formulas that we use depending on whether we know population standard deviation or sample standard deviation. Again, it's Z if we know population standard deviation, and we use T when it's sample standard deviation. So there's a number of different reasons for looking for these differences, but they all boil down to 6 possible hypotheses. So the wording for our null hypotheses could be that the two populations are equal, or there's no significant difference. That would be this first way of showing that symbolically. Or we might say that one population is significantly larger than the other. So this is shown by looking at the difference. If I take population 1 minus population 2 and I get a negative number, that's saying population 1 is smaller than population 2, smaller or equal to. And if I look at the other direction, population 1 minus population 2 is greater than or equal to 0, is saying population 1 is larger or equal to population 2. Alternate hypotheses, we would be looking at the two populations are different, so just not the same. We could be looking at population 1 is significantly larger than population 2. So when I do that subtraction, I get a positive number. Or population 1 is significantly smaller than population 2. Population mean, that is. So when I'm looking at those, I am comparing the differences in the population. So our z-score formula also reflects that. It's the differences in the sample means and the differences in the population mean that go into that z-score. But you'll notice every single one of these possible 6 hypotheses, we have a 0, right? When we're looking at that difference, we're either saying it's equal to 0, less than 0, greater than 0, or some combination of those. So this formula looks a little worse than it actually is, because the mu1 minus mu2 is going to be 0 for every single one of those 6 hypotheses. So let's take a look at an example, and this is using some actual data. So I've cited my source there of the actual data. Compares pockets in men's and women's genes of the same size, and they've got a bunch of data which I downloaded and did a few calculations on. And so we have a mean for the women's of 13.20 and a standard deviation of 1.64, and a mean for the men's of 17.87 and a standard deviation of 3.21. So we're testing this one at a pretty small significance level, right? We're wanting to be pretty darn certain about this. That's 99.9% confidence. And we're told on this one we're going to use those those standard deviations as sigma. So again, when we're looking for, well, what is the wording of our population, focus on that one with the question mark. So the men's pockets are significantly larger than the women's. Note that with these ones, we can kind of arbitrarily pick what we're calling population 1 and population 2, whether it's the men's or the women's. So I can say the men's pockets are significantly larger than the women's. That's the same as saying the women's are significantly smaller than the men's. So I chose my sample mean one as 13.20, which we can see is the women's genes. So I'm taking the women's as my population 1. And likewise, I identified, whoops, not quite that quickly, I identified all of the different values that we have in the question. And then we look again at that symbolic claim. So men's genes are significantly larger than the women's. Since I said women's is population 1, that's saying the claim mu1 minus mu2 is less than 0, right? The women's is less than the men's, which will give us, still got that left hand sign, that's going to be H1, and it's going to be left-tailed. Our H0, as before, and when we're looking at our claim being H1, our H0 has to have the equals in there. So then we can put that into our formula. Got a lot of numbers here, so this one, again, you probably want to pause and try the calculation. So we plug in our two means and be consistent. So since I picked women's as population 1, I'm consistently picking that as my population 1. I showed a few of the intermediate calculations. Definitely you want to show your formula, your substitution, and your final answer, but the intermediate ones, that's optional. Do make sure that you're keeping all the digits in your calculator as you're doing those questions. So we get a fairly high test statistic, minus 8.31, or fairly low if we consider that as negative. So I'm going to do this one using the traditional method, so finding our critical value. We could also do this finding our p-value, both work. So this one, our alpha is 0.001. If you look on your table, you'll find that 0.001 is listed for several values, but they're within a fairly narrow range. They're from minus 3.08 to minus 3.10. So that line here is somewhere around negative 3.09. Regardless of where it is in that range, negative 8.31, way lower, right? It's going to be like right off our chart. So that tells us our test statistic is definitely in the critical region. So even at that 0.1% significance level, there is enough evidence to support the claim that the men's genes pockets are significantly larger than the women's genes pockets. So the other possibility we have is if we do not know those standard deviations for the population, and we assume that they're equal, we can often reasonably make that assumption that these are going to have similar variations. So then we can use the student t distribution. But again, this gets a little weird looking. Also, our degrees of freedom, because we have two populations, we don't just go n minus 1, we actually add up those two populations, whatever, our two samples, for our degrees of freedom. So we have our n1 plus n2, and then we subtract 2 from our degrees of freedom. So that's a little different, and you do have to be careful. But that is on the formula booklet, so it's there to remind you when you're doing your calculation that, oh yeah, remember to use those degrees of freedom. So similar to our z-score, but there's a few significant differences here. So we have this s squared p, or sp squared I should say. So this, it's sort of our standard deviation squared, but we calculate it using both standard deviations from our samples. So n minus 1 from our times s squared for our first sample, and n minus 1 times s squared for our second sample, and then that degrees of freedom is also happens to be our denominator on that. So that SP squared stands for the pooled variance estimator. So the P on the subscript there, remember S squared is variance, but the P is telling us it's the pooled variance. And it is an estimator because we are using a sample. We don't have the population. So the 6 possible hypotheses are still the same as they were before. So no significant difference, or the means are different. Sample 1 is smaller, has a smaller mean than sample 2, or sample 1 has a larger mean than sample 2, looking at our two alternate hypotheses, or they're at least as much as one another, or at most as much as one or the other, depending on which variation we're looking at. So again, we're going to do a quick example of that one. So this one, you'll notice a couple differences. So again, we've got a number of different things that we're looking at. Read through and look for that claim. So this one's a little tricky. The claim isn't in the thing that ends in the question mark. That's more like an intro. It's actually in this statement. It says test the claim that, oh, there's our big hint that there's a claim. So the calcium group had a greater decrease in blood pressure than the control group. Now if you read carefully, the decrease is shown, so on here the minuses are actually an increase in blood pressure because they did not get the expected decrease. They went up instead. So we can see that in these two sample groups of 11 men, each, that we have some fair range on this. But we're not given our mean or our standard deviation for either group. So first thing to do would be calculate those. Quick reminder, you can use the stats function on your calculators and enter in a set of data and get your calculator to find your mean and standard deviation. Another option would be to put those values into Excel, get Excel to find your mean and standard deviation, or if you really like doing things the long way, plug all those numbers into your formula for the mean and for the standard deviation. So one way or another you want to find those values. Again, I suggest you pause and actually get those values before you move on. What they do work out to be, that first group, the calcium group, the mean is 5 and the standard deviation is negative 0.27. For the second group, the control group, whoops, that was not my standard deviation, that was my mean for the second group. And for the standard deviation, it was actually 8.29, so a pretty big standard deviation, but we can see, yeah, it's going from -4 to +18, so we expect kind of a big standard deviation there. In our second group, our mean is negative 0.27 with a standard deviation of 5.90. So we can see there definitely is a bigger difference here, but is that big enough to say it's significant? So question, calcium group is greater than the other group, so I actually am using, instead of 1 and 2, calcium and control. So when we look at that, we're looking at the greater than scenario, so that's going to be a right-tailed test. So our first calculation is that pooled variance estimator. So we plug in each of our sample sizes, -1, so 11 minus 1 is 10. So I already did the -1 in there, times the standard deviation squared. So plug in those values, and we end up with a pooled variance estimator of 51 point, oh dear, I have two different values there. Is the 51.8. This is a mistake. So let's fix that. So we plug that into our calculation. Again, that mu1 minus mu2 comes from our claim, which is where we use those zeros, so that's always going to be 0. That gets to drop off. Our other means 5 minus negative 0.2727, so be careful with those minuses, means plus. Plug in our other values, and we get a test statistic of 1.718. Remember, on these ones, our degrees of freedom, we have to add up the two sample sizes and subtract 2. So 11 plus 11 minus 2 is going to give us 20. We weren't given a significance level, and generally speaking, when we're not given one, we use alpha equals 0.05. So that's going to be the middle column of our t-table. No, it's not, because this is not two-tailed. This is going to be the second column of our t-table. So we go down to 20, and we get a t-value of 1.725. So at the 5% significance level, we can see this is not quite large enough to say this is conclusive evidence. So we're going to say there's not enough evidence to support the claim that the calcium group had a greater decrease in blood pressure. Now, if we looked at our means, they were 5 and negative 0.27, so there was some difference there. So this is not saying there's no difference. It's saying this wasn't a big enough sample size, this doesn't quite prove it. This would be the sort of thing where if you had this study, you would go on to say, we need to do further study. There is some evidence, but not enough. second example, cell phone costs with different providers. So we have two independent random samples. We're given the summary data, so we don't have to calculate them this time. Again, I'm going to suggest try doing this question on your own. Pause the video and continue when you've given it a try. So again, we've got test the claim, and then we've got the claim. The first provider has a higher mean cost than the second. So we're looking at a greater than claim, so right-tailed again. So that pooled variance is the first thing we want to calculate from those two variances we're given. And again, we're given S for standard deviation, not sigma. That's why we know we're using T. We plug those values in for our T, and we get T is equal to 1.892. To find our critical value, we're going to need these two sample sizes. So 23 plus 13 gives us 36 minus 2. We're going to have our degrees of freedom is 34. Alpha is 0.1, and again that's one-tailed, so be careful. It's our first column. So our T is 1.306. So if we look at this right-tailed test, 1.892 is definitely in the critical region that's bigger than 1.306. So we can reject the null hypothesis. As before, when we're rejecting the null hypothesis, right, we're saying this one is wrong, we're supporting the alternate. And since our claim is the alternate, we end up supporting the claim that the first provider has the higher mean cost than the second provider. So we'll pause there. The next video we'll look at how we deal with testing claims of proportions. So it's just going to be a little variation on this one.